So thank you very much, Dr. Ojoy Kumar Kushua, for giving me the opportunity to interact with the people from different parts of country and maybe abroad also through your this first Indo-South Korean joint training school. And also it's nice opportunity to get acquainted with you and your colleagues and your groups. So thank you very much. So today I shall speak on organo-clay systems, how this can be used as a sensor. Okay, so actually, basically, I work on thin films and nanoscience mainly. We do some characterizations then based on some applications. Okay, so mainly we do some optical spectroscopy, etc. Of course, electrical also we do for memory and other things, organic memory. So here I share some of examples we got using clay systems. Okay, so I'll talk something about introduction about clay, then why we select clay or what is the role of clay in this system, then how we prepare these thin films using clay and other materials, and then some few examples, okay, of our recent works. So we all know that soil is always alive with living organism, and it's a complete self-sustaining ecosystems, and without soil, life could not be imagined or considered. And normally sand, silt, clay, organic matter, etc. and other things make up the soil. So we can say that clay is a subset of the soil family, and clay exhibits some interesting properties such as plasticity, and they become soft when mixed with water, again become firm and hard on drying. And due to this, you can see there are several applications like say constructions, pot making, medicinal, cosmetics, etc., and so on. However, we are interested in organo-clay systems. Why? Mainly to manipulate the properties of the organic material so that as a whole the system can be used for optoelectronic applications, maybe sensing also, including sensing also. Now, say, what is clay? So clay minerals represent an important group of layered inorganic solid materials. They swell in aqueous dispersion into single sheet of thickness of the order of say 1 nanometer and diameter, say micrometer order. They have colloidal size, high cation exchange capacities, large surface areas, adsorptive properties, then viscosity and transparency also very high. Another interesting property of clay is that intercalation. That means one can simultaneously incorporate both polar as well as non-polar material within the clay system. So this gives the opportunity to use clay as the novel functional host material to prepare hybrid systems. Okay, so basically this clay, I told you that it's a layered material, and this each layer composed of basically two sheets. One is a series of tetrahedra, schematically shown here. Then another sheet, this is octahedra of say aluminium, then magnesium, iron, etc., something like that. And they organize in such a way that say tetrahedra, then octahedra, then tetrahedra, or something like that. In this way, they form layer, and they stack layer by layer to form crystal. So the basic blocks of the clay are these sheets, either tetrahedron sheets, maybe silica, or octahedron sheet, maybe alumina or iron, magnesium, etc. Okay. So this is just a simple idea of the silica tetrahedron, say this one, and they form sheet like this. And this is alumina octahedron, this one unit, and the repeat unit form the sheet. And sheet upon sheet form layer, layer upon layer form crystals, and layering of this silica and alumina sheets form different types of clay. And also, of course, the composition in between this layer also say makes different types of clay. And mainly 1 silica is to 1 alumina, we say it's TO type clay. 2 silica, 1 alumina, we say it's TOT type clay. So this is a schematic of silica tetrahedron. This is a sheet. This is alumina. This is alumina sheet. Again silica, silica sheet. As a whole, they form a layer. Okay. So this is a layer, and layer upon layer, it forms crystal. So this is some major clay type example. Maybe 1:1 TO type. This is kaolinite group. You can see mica. They are also layered systems. Belongs to clay family. Then say montremolinite. This kind of this is just for an idea. Okay. So swelling. This is an interesting property of clay, because if you have a clay layer or maybe stack of clay layers, then it's possible to swell the system into single sheet, either silica or alumina or magnesium, whatever, maybe of the order of 1 to 2 nanometer. If you put it on aqueous environment or other suitable solvents, then they swell, and it's possible to have single sheet of thickness of the order of nanometer. Main mechanism in swelling is say hydration of exchangeable cations within the clay layers, and at the same time sometimes this osmotic swelling also occur. This is because the concentration in between the clay layer, ion concentration, and the outside within the solvent, due to these two different, the solvents go inside the clay layer and they swell. That means sheets separate from each other and they form single sheets. And then intercalation, it's possible to incorporate different materials within the clay layer or the surface also. It's just in schematic. One can put this material inside the layer, or maybe in the swelled system. This is single sheet, so one can incorporate the material on the surface. This is also possible. This is, say, some polymer intercalated in the clay sheets. Here also you can see this is some clay crystals. It's possible to intercalate at the edge areas also, in between the sheets also. So in this way it's possible. You can see here this is phase separated system. That means clay layers and the gas molecules is outside. So in this way one can play with the systems and at the same time have different property also. Another thing is cation exchange capacity. This is very important. Cation exchange capacity is the interchange between cation in the solution and the cation within the clay surface. In this way one can incorporate other material having different cations attached with this material in the system through cation exchange reactions, and it's measured. The extent of capacity of this exchange is measured in terms of CEC, cation exchange capacity, and this is the total capacity of a soil to hold exchangeable cations. Okay, and this strength is depends. You can see there are so many factors, but there is a series. This is called lyotropic series. So this is the order which one having higher exchange capacity. Then also it increases with the valence and decreases with size also. So in this way one can incorporate gas material within the clay systems. Okay, and CEC is conventionally expressed in mega equivalent per gram. And this is again a schematic to show that this is a clay crystal. This is one layer, this is another layer. So two layer of clay crystal, in between some cations are there. So schematically one can see here in this way. So this way also material can be put inside these systems. So as a whole one can play with the system having different organizations of the molecule within the systems. So we are interested in organo-clay hybrid, mainly nanomaterials, mainly organized in thin films. Mainly our aim is to have properties like sensing, biosensing, catalysis, optics, electronic cells, etc. And also sometimes we are interested to have the property of the single clay sheets, and as a whole to understand the mechanism how this nano composite forms. So as a whole, we are doing this, and recently we are doing some kind of optical switching for optical memory and sensing applications, okay, using this kind of systems. So these are some related works. We have designed mercury sensor, then cholesterol, arsenic, hard water sensor, DNA sensor, etc. These are some supramolecular systems using clay. Now, why this clay organo system is important? This is because the planarity of the pi conjugated system with the confined organic molecules is increased when it's incorporated in the systems, and as a whole it extends the pi conjugation length and hence the electronic behavior. And also the fluorescent quantum yield of the organic materials enhanced. Why? Because when you incorporate the material in the clay systems, it suppresses the vibrational motion of the confined molecules. So quantum yield enhances, and again its electronic behavior changes. And also one can place lot of organic molecules within these systems without aggregations. One can play by controlling the layer thickness, gallery, gap, etc. One can play the organizations in a systematic way. Therefore, as a whole, the organo-clay system show interesting optoelectronic behavior which may not be available in these single organic systems. Here a cartoon I am showing, say this is a film of say clay shown in black, and this is organic material. So in your substrates, clay, then organic material, again organic material may be on clay surface or substrate also. So in this way you can play with the organizations and hence the optical behavior or electronic behavior. Here another cartoon I am showing that if you have a polar molecule and controlling the organization within the clay sheets, you can have resultant moments, say 0. You can see here also, but here if organization is different, so moments not equal to 0 in this way again. So this is a hazard arrangement. So main idea is that one can play with the moments just by playing the organizations. Okay, so how we prepare thin films of organo-clay systems? We use several techniques, say Langmuir-Blodgett technique, self-standing films, spin coating technique, layer by layer cell ensemble technique. So we use these systems because this kind of thin films are of the order of nano or fraction of micrometer. So you cannot, you need sophisticated equipments to do these things. So these are standard techniques we use. These are some LV instruments. It's available in our lab. This is LV with fluorescence imaging microscope facility. This is attached with booster angle microscope. So you can observe the film formation in situ using these two systems. It's available here. So here in this, I just explained how we prepare films. In the machine, we have a trough filled up with some solvent. Normally, we use water. Then we spread the molecule in the surface, and mainly we make a solution in volatile solvents, water insoluble, say chloroform. Then we put the solutions, solvents evaporate, molecule float. Then a barrier, computer control, we can compress like this. Then we deposit, say like this. So if you just compare, say for an understanding, we can say that we all have seen the floating water plant in the pond or somewhere. If you compress them with a bamboo, same thing happen here. You just allow your material float in the surface. You compress with a barrier. Of course, if you at a time will come when molecule will touch each other, just like water plant. If you go on further compressing, then system will break. So here also same thing. And how we deposit, say if you heat milk, you will see a layer cream form. If you dip a spoon and take out, you will see some cream stick on the surface. So same process here we apply. And by discovering this technique, Langmuir got Nobel Prize in 1935. Okay, but the thing is that here the order of thickness of film is ideally single molecule thick. So it's easy to say, but very difficult to make a very good film, because a minute flow of air, maybe breathing, or some amount of dust may change everything, may change the property of your system, because you cannot see it in direct way. You have to control, you have to manipulate, you have to understand the organization. So this is the thing. For preparation of organo-clay system, what we do, we prepare clay dispersion in water, following magnetic stirring, then ultrasonication, then we put in LV trough, then we put some organic material, mainly cations, on the surface, allow time so that they can come onto the surface through cation exchange reaction or electrolytic interactions. Here we have shown. Then we compress, then we deposit. So in this way we do these things. Yeah. So during this film formation is a time-depending process. Say your clay is in this surface, and in the surface your organic material. So with time they come. You can monitor these things by infrared reflection absorption spectroscopy. So you allow a light to fall on the surface, and if you measure the reflections with time, it will increase. Okay, so if you have a plot, you will see this is the silicon SiO vibrations of the clay, and you see the intensity of the band increases with initially with time, and after some times it flattens. That means all clay systems come to the surface. Okay, and with AFM also you can we have monitored. Say this is a film deposited after 5 minutes, and this is 30 minutes. You can see high density. So in this way you can have idea about the reaction kinetics. And here we prepare self-standing films. This is we prepare mixture of the clay and organic systems, do ultrasonication, and then we have a suction systems. We use some membrane here, sometimes cellulose PTA membrane of a fraction of micron pore size here. Then we put the mixture here, we suck with vacuum pump, then film form in the membrane, and we can peel off the film from the membrane. It's self-standing. Okay, then spin coating, you all know that it's based on the rotations. You give the drop solution here, then it rotates and it's form films. But here control is very less. It depends only speed of rotation, concentration, time of rotation, etc. But it's possible. And we also prepare layer by layer self-assembled film. This is through electrolytic interactions. We use dispersions of clay here. Then we dip a substrate which is charged and of course oppositely charged. Then they will interact here, and you see organic materials attached here. Then we dip in the clay, and alternately it's a clay organic system. So it's a self-assembled systems, layer by layer depositions. This is a representative images of AFM by AFM of the different clay. This is saponite, leponite, Wyoming, hectorite. This is again saponite. You see all are nano dimensional, nano order. So here one example I share with you. So this is a iridium molecule. It's a synthesis by our collaborator. So we prepare a self-standing films using this and clay saponite. Okay, so this is the photographic image just with a simple camera. This one as prepared. Then what we did, we put a drop of some solvent. We use DMSO and we make it wet. That is, it is swollen. I told you that one important property of clay is swelling. And then we observe with normal light, you can see no color change. But when we expose the swollen film under UV, you see the color change. This is different concentration of clay. You see the color change upon UV, but normal light, it's as it is same. Okay. Then we analyze why this thing happened. We measure the spectroscopy, absorption, and fluorescence, and we see that during swelling, the fluorescence shows longer wavelength, broad band, which is mainly some kind of specific aggregation related to excimer, that is pi stacking of one ground state molecule and one excited state molecule. Then we analyze further and measure the lifetime, and we have seen that the lifetime of this longer wavelength broad band is several times, 18 times longer than the monomer fluorescence. And this is the characteristics of excimer formation. Also, we studied the XRD and measured the gap between the layer, and we have seen that in case of this film dry, the gap is of the order of 0.48, but when it is swollen, the gap is 0.93. So this is almost double than the single thickness of the molecule. So we consider that pi stacking order and swelling conditions forming excimer, and this is mainly and you know, excimer is the excited state phenomena because one ground state and one excited state molecule. So only fluorescence color change is occurred, not UV, not during absorption. So naked eye, no color change. So here I am showing this is as prepared, this is swollen. This is again after swelling, what we did when we expose UV, you see the color change. Then again we wash the film to take out the DMSO. Again you see the original color come back, and then dry, so original come back, and it's a reversible process. And we checked it more than 50 times. We tried, and it's possible. It's schematically here shown. You see in dry condition single molecule flat, but in swelling you see more than one molecule stacking. It's an independent of solvent also. Even with water also this is possible, but we use DMSO due to high boiling point, so it remains longer time. So we propose this can be used for secret writing. How? So this is our say as prepared film. We with a hearing bar we write say TU on the film, and then we observe with naked eye with ordinary visible light, no color change, nothing is observed. But when we expose it under UV light, you see that TU is written. That means it can be used for secret writing. Again, washing, dried, original color come back. So it's a very good supramolecular systems. Then again, this is another clay and indolil systems. You see freshly prepared, no color, but when we dried it due to aerobic oxidation, red color occurred. But in swelling conditions, twisting of the bonding occur and conjugation affected, so color changes. And we observed that this is for different concentrations, and we observed that this is again reversible. You see, so this is very good for optical sensing. And main issue is it's with naked eye one can feel the change, the sensing. This is important. So schematically here we have shown this is in dry condition, this is in freshly prepared. Then in dry conditions, you see it's red, and also we measured with XRD the thickness. You see here it's less, so molecule is almost flattened, and this will extend the pi conjugation also. So red color occurred, but when we swell, you see gap increases and twisting occurred here, so color changes. So this is a reversible process. Okay. This is another example. This is a clay and polydiacetylene, a polymer. Also, this is a freshly prepared clay polydiacetylene films. You can see no color observed. Okay. We use self-sending this suction system. This is on a membrane. It's a paper film kind of thing. Okay. So this is some informations. So polydiacetylene, mainly this is a diacetylene monomer. When they align, organize in specific arrangement, say angle of this one and this of the order of 45 degree and distance of the order of this, then upon exposure of UV, polymerization occurred. Okay, so this is the polymerizations. Then again, if you expose with further UV or temperature or other stimuli, it will twisting here occurred, and orientation changes. An interesting thing is that these two states in polymerized PDA is different. This is blue color, and spectroscopic feature also independent. And here again red color. Here also spectroscopy is different. I show here. You see, this is the monomer. This is black flat line. When we polymerize with UV, this red color, this is in blue phase. Okay. Then if you expose it with some external perturbations, you will see this red phase. Okay. And it's visible with naked eye. And you see the spectroscopic feature is also different. And in fluorescence, you see this flat line black is monomer form. Even blue phase also no fluorescence, only red phase fluorescence. Okay. So we can say that PDA has two phase. One is metastable blue phase, another is red phase. So with playing environment, one can switch between these two states, and hence it's a very good material for sensing applications. Okay, so we used these organo-clay systems for designing various sensors, say volatile organic compound, gasoline adulteration, then pollution level in car exhaust, alcohol sensor, etc. So for this, what we did, we make a self-standing film of a polydiacetylene clay, and then we also tried with PDA clay. This is one system. Then PDA clay and another organic material. This is synthesized by our collaborator. This is imidazole. So it's a two system. One is clay and PDA. Another is clay, PDA, and imidazole. Okay. So this is how we prepare again self-standing film on a filter membrane. And after UV, you can see the color. This is blue phase. So what we did, we prepare both PDA clay film or PDA clay imidazole film on the membrane, and then we expose upon UV, converted into blue phase. Then for VOC sensor, it's a self-prepared systems. We make a lead in a simple beaker, and inside the lead we put this blue film. Okay, and we kept VOC here under in different volume ratio, and with time we see that the color changes. It converted into red. You can see we tried with 12 different VOCs. Okay, toluene, benzene, in this way, say with DMSO, hexane, THF, so many propanol, ethanol, methanol, etc. So we tried as a whole 12 different organic compounds, and we found that almost all these compounds respond, our sensor responds to all these components. But of course, the response is depends on the, you can see different concentration of the analyte, concentration as well as exposure time. So one has to play with these things to have a real sensor. But good thing is that it's responded. But you see the extent of color change is different, although one can have a sensation of response, but it's difficult to quantify. To do that, what we did, we using a simple MATLAB program, we recorded the RGB value from this photographic image of this colors. Okay, and then we analyze the normalized signal intensity, which is red versus blue divided by R0 B0, where R0 B0 is the component of red and blue before the exposure, and R and B is after the exposure. So if the normalized signal intensity is increasing, that means your extent of polymerization from blue to red is higher. So in this way, one can quantify, and you can see we have plotted this normalized value with different concentration, and you can see it's so linear. So one can have a good idea of quantifications about the sensors. Then we apply these systems. This is TCDA clay and also TCDA clay and imidazole for sensing of gasoline. This is normal petrol. We collected petrol from the market, and you see we put petrol here, and then we make our film through UV exposure into blue. Then we put the film here, and you can see based on different volume ratio, you can see the color changes. Okay, so for both TCDA clay as well as mixed films, you can see. And then we analyze the normalized signal intensity, and you can see the plot. It's almost linear with concentrations. So, and here, of course, it's beyond these concentrations, beyond 5 for TCDA clay is linear. Okay, so one can have idea about these things. Then we applied this material to check whether our gasoline is pure or it's adulterated with some other material. And normally in locality they use kerosene to mix kerosene with the petrol, because kerosene is cheaper. So what we did initially, we checked, we have observed that when we expose our blue phase film on petrol, it's converted to red. Okay, so from here we optimized most probably 10%. So we, for 10% case, we mix kerosene at different ratio. You can see here the ratio, and then again we expose our blue phase film in this adulterated petrol, and here you can see the extent of polymerization is less. That means presence of kerosene affected the phase change from blue to red. And here you can see with increase in kerosene concentration, this is you're decreasing the extent, and up to beyond this concentration, polymerization is not possible. Okay, so it can give an idea whether our petrol is contaminated with kerosene also. Then we extended the applications of our design systems for checking the pollution level of car. So this is a very simple process. How we did it, we prepare the film, then we make it into blue using photopolymerizations, exposure of UV light. Then this blue film is kept here, and we start on the cars and kept for different times. You can see immediately after start on, depending on the presence of the components of the exhaust, you see color change occur. This is for one car. We checked for several cars. This is a representative figure. You can see with 5 seconds system started changing, and you see it's totally red phase. Then we you can see these are some comparison of 2 cars. Okay, this is car 1 and car 2 at different times. You can see we initially converted the PDA films into blue phase. Then we put the car silencer, and you can see after 30 seconds for the 2 car, and the extent is of change is different. But for quantification, we analyze the normalized signal intensity, and you can see the comparison of 2 cars. One is black, one is red. You see for car 2, red is in all time extent of polymerization is higher. Okay. Then we checked the pollution level of the car using standard system available in the market, and we analyze the components available in the car exhaust, say CO2, CO, HC, O2, etc., and compare for both the car. And we have seen that based on the concentration of CO2, CO, HC, O2, etc., here polymerization linearly affected. So that means with proper calibrations, it's possible to have idea about the exhaust level of car or pollution level in the car exhaust. Okay, using our this clay organic PDA as well as imidazole systems, and it's simple a paper kind of things. Then we applied the same systems for, no, this is a different systems, different clay and other material also. This is an most probably imidazole, most probably it's a imidazole, clay and PDA, and here the clay is most probably hectorite. So this is we prepare a self-standing film using the similar suction systems. Then we expose it under UV light, converted into blue. Here you can see the image. Then what we did, we kept the film in front of a person who consumed alcohol. Okay, and he used to give puff in the film, and you can see the color changes just based on the breathing, maybe breathing or something like that. You can see film after 5 times puff, after 1 hour of consumption of 2 pack alcohol, you can see the color change. So interesting thing, it's something like litmus paper. Just observing color change, you can have idea that at least, yes, people is drunk. Okay. So, and quantification, again, for quantification, what you have to do, you have to take the photographic image, then analyze the RGB value, then you can quantify how concentration of alcohol affects the extent of polymerizations, and you can have some idea. But the thing, good thing is that only a piece of paper kind of thing you put in front of a drunk person, and you can just observing color change, you can have an idea at least that yes, he is drunk. And this is some representative image you see before exposure of the person of the film. Before the person, you see it's an fluorescence microscopic image, and here you see the polymerization occur after this puff by the drunk person. You can see the polymerized structures. This is just a idea that how structure changes based on the presence of alcohol. So what I want to say is that, say, normally in market, alcohol sensor, most of the things are based on resistivity change or conductivity. So for this, you need battery, you need say ammeters to measure the current, battery to apply the biasing, then the resistivity of your material changes, and you calibrate the conductivity with the concentration of the alcohol. But the issue is that it's a costly system because you need battery, you need these things. But in our systems, it's a simple piece of paper. Okay, so without any help of any sophisticated machines, you can prepare this paper, and you can just by observing the color change, you can have idea about the sensing. So that's similar to a litmus paper. So it's very easy and interesting also. So as a whole, I conclude saying that clay materials, it's an inert and it's a natural material, but of course now synthetic clay is also available. So very promising for preparing organo-clay hybrid supramolecular structures, and this kind of materials is very promising for future technological applications, especially towards designing various sensors. Okay, so here I have shown only few representative results. If somebody of you are interested, then you can visit our group website or in the university website or our personal website and have a look about work, and you can contact with me also. With this, I conclude, and if someone of you have any query, you can ask me or we can interact. So thank you. Oh, okay. So this is my students. They helped me to have these results, and this is the funding, and these are the collaborators for these organo-clay systems. With this, thank you all for your kind patience. Okay.
So thank you, Professor Hussain. Really excited us. Lot of interesting results are there, and I hope participants also enjoyed the discussion. So now floor is open. If anyone has any query or anything to discuss, either you can write your question on chat box, otherwise you can raise your hand and we can unmute. So the talk is open for discussion. Meanwhile, let me share at least one or two queries with Professor. So, see, one of my queries is that all of these systems, whatever you have shown, they are self-standing or they are having some support of substrate?
Actually, self-standing because we prepare it on the membrane, and then with the help of forceps, etc., you can take it, peel off, okay, and it's
Okay.
self-sending because this clay material is used as a, you can say that, to hold the whole systems, okay. So it's self-sending systems.
Really, your this secret writing was very interesting. I just looked like it's given a new thought to us. I was having one query there, like how long we can retain that writing? Like how longer? Because as you said, after drying, it is not going to have that write up, right? Once
Yes,
you
yes,
dry.
yes.
So
So
let's.
actually, this is mainly based on, you are playing with the gallery gap. I mean, layer gap of the clay. How? When you dry, water molecule come out, so layer thickness decreases, and it affects the molecular organization. I mean, flattening. So color changes. Okay, and when you swell, means you increase the gallery height. Then in that particular case, we have seen that stacking of two or more molecule occurs. And this stacking, there are so many issues for aggregations, and here it's formed excimer. And excimer is some kind of aggregations where pi stacking of one ground state and excited state molecule, and it's an excited state phenomena. So when you don't see any change in absorption, it means naked eye. But when you check the fluorescence, you see the change. Okay. So here, when we expose under UV, then we see the change. So in this way, we propose for secret writing. But yes, the question is very perfect because it's based on some kind of solvent. So as long as your solvent is there, you can have your system in swell conditions. Otherwise, it will not.
So
So
as per your analysis, how long we can retain the writing? Like how many days or month? If we are just keeping in normal atmosphere.
normally it depends because if you use DMSO is boiling point is very high. So as long as the solvent is there, so you will see it's there. And normally we have seen that the color is several month color is there. We have observed this. Okay. And in second example, in that case, also we have, because this is change is observed in naked eye. So both color, we have seen that it persists long time. But of course, you have to preserve in a proper way so that your solvent is there.
Yeah, yes.
Otherwise, it will be difficult. So it needs some kind of optimizations, some kinds of further research, some kind of further play, how to put this in real, applications.
So we are having one question on chat box. If you can see, otherwise I can read for you.
Uh,
Uh,
you,
it
you
is
please
from
read.
Surya Tiwari. He's asking, sir, comparing the normal alcoholic sensors and the clay PDA film, what are your view on the accuracy? Are there any external agent like moistures in the air that can affect the outcome while checking on the similar results?
Yes, yes, this is very interesting because moisture always affects, because your moisture sometimes swells your film.
Yes, yes.
So your environment is very interesting because you are actually you are playing with the microenvironment. So you have to make an arrangement so that uh, because there are some examples where people use these systems as a moisture or a humidity sensor also. You prepare your systems, put it in a somewhere, and based on the humidity change, you can see the color change. So if you want to have idea about other, materials or other contaminants, then you have to make sure that your moisture should not affect. Otherwise, of course, there will be error. And regarding accuracy, you have to optimize, because always whenever you are designing sensor or any machines, you see sensitivity depends upon your applications, up to what extent accuracy you want. So in this way you can play, you can design, you can manipulate. Of course, if you want very high sensitive systems, then you have to work very hard and you have to optimize and the things in a very proper way. Otherwise, it's okay. Just observing color change, you can have an idea.
So, Professor, in similar line, I'm also curious to know one more thing. Like,
Yes.
about the reusability. Can we reuse the strip again after
Yes,
it's dry?
yes. This is because in all the cases, I showed two examples here. Both the cases, we have seen that when we swell the material using some solvent, say DMSO. So normally in ambient conditions, it's not going out. I mean, evaporate because very high boiling point. So what we did, we washed the film with water. Okay, then we dry it. Then original color come back, and we have checked it, say, in one case more than 50 times. It's reversible. That means it's reusable. So, and in another case also several times we have checked it. So it's reusable somehow.
It's very interesting for us. So, if any participant would like to discuss, still we have a couple of minutes. Anyone, if you want to speak, even you could let us know. So I think we already interacted a lot. Many queries I think is already resolved in our discussion. So if
Yeah, thank you.
no more questions are there, then let's thanks Professor. So as usual, I request Vasundhara. She will thank you to Professor Hussain. Vasundhara, up to you now.
Thank you very much, sir. So I take a moment to thank Dr. Hussain. This was really an interesting talk. On the behalf of Indo-South Korea JNC, I thank you for sparing your precious time to share some valuable insights on organo-clay supramolecular assembly with all of us. I'm sure all the attendees would have learned a lot from your session. So once again, thank you, sir, for joining us and giving us some valuable insights. Thank you, sir.
Thank you.
Okay, so thank you, Professor, for joining
Thank you,
us.
sir. So it's nice. We'll be in touch somehow, maybe.
Yes.
Sometime.
It
Thank
was
you.
very interesting, yeah, really. So thanks a lot, and I hope you will also participate in other lectures. Maybe you will encourage your students and your group to join some of other lectures. And once again, thank you very much. And Vasundhara, maybe now move to